Welcome to today's Explainer. We're going to uncover exactly how intense, external physical forces traumatize the human body. But we aren't just looking at the damage. We're also going to explore how our incredibly resilient biology actively fights back to heal itself. It's an amazing process, so let's dive right into the mechanics of injury.
Here's a quick look at our learning objectives. We'll start with a brief intro to physical injuries, then tackle extreme heat and cold, electricity and pressure changes, and the complexities of radiation exposure. After that, we'll map out the wound healing process before wrapping up with our main takeaways.
All right, let's jump right into our first section, an introduction to physical injuries and understanding the external forces that cause them.
Now, when we hear the word injury, we usually think of a simple cut, a scrape, or maybe a fall. But physical trauma goes way beyond that. In this session, we're focusing on systemic trauma, damage that is categorically driven by extreme environmental forces. We're talking about extreme temperature exposure, severe electrical currents, sudden atmospheric pressure shifts, and that totally invisible threat, radiation.
Moving on to our first major category of trauma, let's look at temperature, specifically the absolute extremes of environmental heat and cold.
When someone is exposed to extreme low temperatures, imagine a worker accidentally trapped in a commercial freezer or someone stranded out in brutal winter conditions. The body's own defense mechanism actually drives the injury. Blood is instantly diverted away from the skin. Why? Because your body desperately wants to protect your deeper, vital organs. But this causes something called anoxia, which is a severe lack of oxygen in those surface tissues. So what starts out as a superficial frost nip quickly snowballs into full-blown frostbite, damaging the skin, ruining small blood vessel walls, and eventually leading to gangrene.
On the flip side, let's talk about the opposite extreme, burns. A first-degree burn, kind of like your standard annoying sunburn, only affects the very top layer, the epidermis. You get some redness and maybe a little edema or swelling. But as we step up to a second-degree burn, that damage penetrates down into the dermis, causing severe, incredibly painful blistering. Finally, the third-degree or full-thickness burn literally destroys all layers of the skin, burning right down to the underlying fat and muscle.
Now I want you to think about this scenario for a second. A patient is rushed into the emergency room with a severe, leathery, blackened third-degree burn. But strangely, they tell the doctors they feel absolutely no pain in that specific spot. How is that even possible? Well, it happens because the burn is so devastatingly deep that the pain receptors themselves, along with the sweat glands and hair follicles, have been entirely obliterated. The sensory hardware is just gone.
So, that brings us to our first key takeaway. Temperature extremes absolutely destroy tissue, but they do it in two entirely different ways. Extreme cold destroys via oxygen starvation, or anoxia, while intense heat directly and physically obliterates those tissue layers.
Okay, let's shift gears to our next section, electricity and pressure changes. We'll be navigating how currents and blasts interact with our biology.
Electricity is fascinating, but it's only harmful to you if it actually completes a circuit. For damage to happen, there absolutely has to be a contact point of entry and a discharge point where that current exits the body. If a construction worker touches a live wire but happens to be perfectly insulated from the ground, no current flows. No circuit, no injury. But the moment that circuit is made, watch out. The current travels deep. We aren't just talking about surface burns. These currents ravage subcutaneous tissue, muscle, and even bone, causing deep fourth-degree char burns. And it gets worse. This deep destruction releases toxic materials from the dead tissue straight into the victim's bloodstream.
What about sudden massive changes in pressure, like an explosion? Interestingly, the medium you're in dictates the type of injury you'll get. If you're caught in an air blast, the explosion violently squeezes your body, sure, but the real villain is the sudden wave of negative pressure that immediately follows. That negative pressure overexpands and literally ruptures hollow internal organs like your lungs and intestines. However, if you're in a water blast, say you're floating in a lake when an underwater detonation goes off, you might just pop right out of the water like a cork. And because of that displacement, you could potentially escape serious internal injury altogether.
The essential takeaway here is that electrical damage is dictated entirely by the path of the current making a circuit, while blast injuries are completely dictated by the environment, whether air or water, compressing and expanding against the body.
Let's tackle our fourth topic, and it's a tricky one, understanding radiation. This is the invisible cellular threat.
The true, terrifying danger of radiation comes down to one word: ionization. Ionizing radiation,
things like gamma rays or X-rays, pack so much energy that it actually alters the positively or negatively charged particles deep inside your body tissues. This intense chemical alteration damages your critical enzymes, and worst of all, it destroys the delicate DNA complement within your cells. And you know what happens without intact DNA, right? The cells are completely unable to survive or divide, leading to widespread tissue death.
Now, trying to measure this invisible threat can feel like alphabet soup, but keeping these units straight is crucial. Rontgen simply measures the intensity of the ionizing ability in the air around you. It's about the environment. But Gray and Sievert? Those measure the actual radiation dose that has been deposited into human matter. The Sievert is especially brilliant because it adjusts the math based on the effectiveness of different types of radiation and how sensitive your specific human tissues are to that damage.
In any medical or industrial setting, you absolutely must know the difference between contamination and irradiation. If you go to the hospital and get a diagnostic X-ray, you're being irradiated. There is no direct contact with radioactive material. Once that machine turns off, the exposure is over. You are not radioactive. Contamination, on the other hand, means you have physically retained radioactive material. Imagine accidentally inhaling radioactive dust at a processing facility. That material gets deposited deep inside you, like in your bone marrow, and it just continuously emits radiation from the inside out until it decays or can somehow be removed.
So, where is all this radiation coming from anyway? Well, the truth is, we safely encounter natural background radiation every single day of our lives. We get bombarded by cosmic rays from space, especially if you live at high altitudes or take frequent airplane flights. We also absorb it from radon gas that naturally decays in rocks. But the significant, potentially dangerous exposures, those almost always stem from man-made sources. Think targeted medical imaging like CT scans, highly focused radiation therapy for cancer, or those rare but severe industrial radiography accidents.
Our key takeaway for this incredibly complex module is this: the actual severity of a radiation injury basically boils down to three things: how deeply the radiation penetrates, how much of your body is exposed, and exactly how long that exposure lasts.
All right, we've talked a lot about the damage. Now let's look at the fix. Section 5, the wound healing process and the body's biological rebuilding.
Your body is effectively its own biological construction crew. When trauma happens, it instantly orchestrates recovery through 4 distinct, beautifully overlapping phases. The process starts right at the surface, with a massive immediate response to stop the bleeding, and over time, it works its way all the way down into deep tissue repair. Let's break down exactly what this construction crew's doing. First up is hemostasis. The body immediately forms a blood clot at the top of the wound to plug the leak, fast and efficient. Next, we hit the inflammatory phase. That blood clot hardens into a protective scab, while tiny, specialized cells called macrophages sweep in like a microscopic cleanup crew to clear away dead cellular debris and bacteria. Then, the real heavy lifting begins in the proliferative phase. Fibroblasts multiply rapidly to rebuild the underlying subcutaneous fat and tissue matrix. Finally, the remodeling phase wraps the whole thing up, leaving you with a completely, freshly healed epidermis and dermis. It's a highly structural, perfectly timed operation.
And that brings us to our final section, summary and takeaways. Let's quickly review everything we've accomplished in this explainer. Think about how much ground we just covered. We've successfully categorized the massive external forces of injury, completely understanding how cold causes anoxia and how heat directly destroys tissue layers. We learned that electrical current needs a complete circuit to cause those dangerous deep char burns, and we saw how blast injuries depend heavily on whether you are surrounded by air or water. We demystified invisible ionizing radiation and its measurement units, and finally, we mapped out exactly how the skin manages to rebuild itself in 4 distinct phases.
I want to end our session today by passing the baton directly over to you. Now that you know exactly how these specific external forces ravage our biology on a cellular level, how are you going to apply these concepts? Seriously, how can you use this deep, mechanistic understanding of injuries to anticipate hazards, elevate safety protocols, and ultimately protect yourself and others in your own specific environment? I want you to keep that exact question in mind as you head back into the real world. Thanks for hanging out and learning with me today, and I'll see you in the next explainer.